Howdy, my name is Andrew Weir, and along with Sarah Goulian, we made Reality Radar, our final project for CSCE 439 data analytics for cybersecurity. The news is incredibly important in our lives, whether it's checking the weather in the morning or something a lot bigger, like finding out about a global pandemic. The news is very important as it informs us of what is happening around us and how it may impact our lives. And with the advent of online news in the past couple of years, there's been a shift. It is now easier than ever to spread fake news in order to manipulate people. This is couldn't be more clear than the 2016 presidential election, where fake news had 1.5 million more shares than real news. In this election, fake news was becoming increasingly popular, and companies like Google and Facebook were realizing that it's even more profitable because more people are sharing it. Fake news has been a problem and it will continue to be a problem. One of the more interesting things about fake news is something called the Underwich hypothesis, which really led our project. This is originally a psychology principle that suggested that the idea of real experiences and recalling that memory is significantly different from the memory of fake experiences. How this works with cybersecurity, at least in theory, is that fake articles should significantly differ in style to real articles, and that you could use that difference in order to suss out which are real and which are fake. For the related work, there are four main types of fake news detection algorithms. The first uses fact checking, which is checking the claims in a news article against a fact bank. This fact bank can be made automatically or manually by a team of experts or by crowdsourcing it. Fact checking is very useful for these types of algorithms, but it's hard to verify facts. And when facts are coming out, the news is very fresh. It's hard to verify facts because they're brand new. Style-based is detecting fake news based on how it's written. It's great for timeliness, and it works very well for the sort of clickbaity, sensational news fake news is well known for. But it ends up turning into a game of cat and mouse where the researchers will come out with a new algorithm to detect fake news, they'll prevent it, and it keeps going infinitely. Propagation-based is based on how a news article spreads. Fake news, statistically speaking, spreads faster than real news, especially when it comes to political stuff. And so based on that temporal data, you can figure out whether a news article is true or not. Not only based on temporal data, as in how fast it's spreading, but how many times it's been spread and who it's been spread to. It's less cat and mousey than the style-based, with some of the same benefits, although it's also pretty bad for timeliness. The final one is source-based. A pretty useful one, but not very good on its own because its only data collection is who published the article, where they published it, and who the publisher was. Most of the papers written nowadays use at least one, if not more of these. Fake detector used both a source-based and style-based in order to form a sort of credibility score. Another paper called A Sensitive Stylistic Approach used both fact-checking and style-based in order to suss out Twitter threads about politics. N-gram analysis and machine learning was a very influential paper on our research. It used 6 different techniques, all style-based, in order to determine fake from real articles. Another one called fake news early detection focused on being as fast as possible. So along with N-gram analysis, it used strictly style-based, just to be as fast as possible. So for our methodology, we decided to collect our data from Kaggle. The main 2 reasons were because it was a supervised data set and already labeled. The other reason was because the N-gram analysis paper that I mentioned earlier used the same data set. The next thing we had to do was data cleaning. This is getting rid of stuff like Twitter handle, usernames, special characters, links, dates, stop words, and we also performed stemming, which is to reduce the complexity by shortening a word into its base forms, like the word running or runner, which is turned into run, that sort of thing. Our approach, the first was TF-IDF, which is term frequency inverse document frequency. This turns a string into a frequency based on how important the word is in the series of documents. It's generally better than the other type of vectorizer we used, called a count vectorizer. A count vectorizer turns a set of strings into a frequency, but only based on the count, whereas the TF-IDF is also based on how important it is in the document. The 2 types of algorithms we used were random forest. Random forest classifiers use an ensemble of weak learners that vote on each data set given, and so they become a strong learner together and a support vector machine, which slices data to find the distinction between them using hyperplans. And so in the end, we used 3 different types. We did a random forest with TF-IDF, a support vector machine with TF-IDF, and a random forest with the count vectorizer. Here's our results. So as expected, the count vectorizer random forest did the worst. That's because TF-IDF is just generally better. Interestingly about that, the reason it was so bad is because the false positive rate was really, really high. For our random forest with TF-IDF, it was significantly better. And for our SVM with TF-IDF had really, really good results, 99.3%, almost too good. There might have been some potential data problems, features that only fake data had or only true data had, so that the SVM could suss them out so efficiently. And also might have been because we only used one data source. So in future work, we would want to use more data and use it from multiple sources to avoid problems like this. Perhaps using an SVM with a count vectorizer, or using other types of classifiers like gradient descent or kth nearest neighbor, along with cross-validation.